This talk is Breaking Crypto Without Keys, Analyzing Data in Web Applications, in case you're in the wrong place. Quick intro about me. My name is Chris Ng. I'm the Director of Security Services for Veracode. We are a startup specializing in the application security space, and you'll probably hear more about us in the coming months. The past 6 years, I've been a consultant for AtStake and Symantec, specializing in penetration testing of web applications, networks, products, and whatnot. And prior to that, I was with the Department of Defense. A few quick assumptions that I'm going to make with this talk. The intended audience of this talk is primarily penetration testers, but it's going to also be useful to any of you people who are doing application development. It kind of helps you understand some of the things you might be doing wrong with regard to your crypto, and some of the things that a pen tester might be looking for. I'm assuming a basic understanding of cryptographic concepts at the very highest level. I'm no cryptographer myself. You really just need to understand kind of, what a cipher is, difference between a block and a stream, things like that. But you don't have to understand any of the math. And I'm going to actually do a little quick refresher a few slides in. So quick agenda, we'll talk about the problem statements that we're trying to solve here, do the quick crypto refresher, go over some high-level analysis techniques for looking at data, and then the bulk of the presentation is really centered on the case studies. And these are real-world examples of penetration tests that we've done in which we've come across unknown data and how we kind of went about that process of figuring out what it was and then getting to the point of identification all the way up to a working exploit for the application. And if we have time, Q&A. This was originally a 75-minute talk, and it's a 60-minute block, so if I talk really fast, I apologize. I just want to get through as much of the material as possible. So the problem is this. What do you do when you're doing a web application pen test and you encounter unknown data? So that can be any number of things. It can be a cookie that gets issued by the application. It can be hidden fields or get post parameters that get sent back and forth between the browser and the application server. Sometimes these things are very transparent. They're ASCII, they're readable text. Other times they're just what we like to just call blobs of stuff. And it's not evident just looking at them with the human eye what they are. And what you really want to know is this something that I can even try to attack? Is this encrypted? Is this weakly encrypted? Is this just trivially encoded, and maybe it's something that I can easily reverse? Is it just a simple XOR with some static string? That's the main question we're trying to answer, so we can figure out to focus our efforts on this unknown blob, or to move on and find something else that's more appealing. The other question, how much do I really have to know about cryptography in order to exploit crypto implementation weaknesses? And I'll answer that one now, not very much. If you kind of know what some of the common weaknesses are, you really don't have to understand too much about crypto. It comes down more to pattern recognition and some basic high-level analysis techniques to recognize some of those flaws. So our goals are to understand those techniques, understand and recognize the characteristics that I referred to, and then apply those techniques to real-world pen tests. A lot of people just talk about theory, and I personally, I learn best by example, so that's why I've tried to design the talk in such a way that most of it, after I talk about the high-level concepts, most of it really is looking at the real data and breaking it down and showing you what we found, and hopefully that helps illustrate those concepts. Okay, the quick refresher. I'm going to breeze right through this. Two types of ciphers, block cipher and stream cipher. Block cipher operates on groups of bytes at a time, so you may encrypt 8 or 16 bytes at a time, given a certain algorithm. Block sizes can vary based on different algorithms, and block ciphers usually have different modes of operation for encrypting messages that are longer than the basic block size. So for example, if you have a 128-byte message, you encrypt it in 8-byte chunks, but there are different methods that you can use to put those blocks together. And we'll talk about one of the very weak modes that we're going to be looking to exploit. example ciphers that are block ciphers that you probably all recognize. A stream cipher is going to operate on the plain text one bit at a time. Usually what happens is there's a key stream that gets generated through the algorithm, and that's independent of the message data. And then what you do is you combine it with the plain text, usually with an XOR, to encrypt the data, or you XOR it with the ciphertext to decrypt. RC4 is the most common example of that. So the first block cipher mode that we're going to be looking at, and this is the weak one that we'll be talking about later, ECB mode, electronic code book. In this mode, every block of plain text is encrypted independently of one another. So what this means is no matter where that piece of plain text falls in the overall message, it's going to encrypt to the same value, whether it's the first block, the last block, or anywhere in the middle. And you can see the kind of the diagram there. There's kind of no linking between the blocks. Each piece of plain text just goes into some encryption mechanism. The key goes in, and out comes ciphertext. The problem with this is that, first of all, structure in the plain text is reflected in the ciphertext, and I'll show you an example of that in a second. And the other weakness is that ciphertext blocks can be modified without detection. If I change something in the ciphertext in the overall message, that doesn't affect any of the rest of the data. So I have no idea that the message was really altered. Here's the textbook example of ECB mode, courtesy of Wikipedia. This is an image encrypted with ECB mode. And so you can see on the right side, a particular color, I guess, is always encrypted a certain way. So no matter where it is in the diagram, it always looks the same. So you can see how the patterns in the plain text data are still very evident. And we're going to carry that technique over to the web applications. The other block cipher mode that I want to talk about is CBC. This is a more secure mode in which, if you take a look at the diagram, what happens is each block of plain text is XORed with the previous ciphertext block before it's being encrypted. And the result of that is that each block of ciphertext is influenced by everything that came before it. So in doing that, if you alter one thing in the ciphertext, you've altered the rest of the message. So you can't, it's not just a simple codebook type operation like the previous mode. This is something that we're not really going to have many attacks against, but I just wanted to mention. There are a couple other block cipher modes as well that are similar. They use chaining in different ways, but I'm not going to spend too much time on that. And finally, the stream cipher operation. Like I said before, this is usually a basic XOR operation. You take the algorithm, pass the key into the key scheduler, that generates a key stream, and then you combine it with the plain text to get the ciphertext. And the key stream is essentially infinite. You just keep generating for however much plain text that you need. Okay, so our analysis techniques. This is something I want to put in here, but it didn't really fit anywhere else. So just in general, common methods of structuring data in tokens. When you're looking at structuring, putting a bunch of data into a single token, there are a number of different ways that it can be organized. And this is just kind of getting into the mind of the developer and thinking of, what is going to be the underlying construct of those cookies or those other tokens that we're looking to analyze. So sometimes it's fixed length data. If there are known lengths of data that are being put into the token, you might use 6 bytes, 6 bytes, 6 bytes. You might use variable length data with a separator character in between them. So like a pipe or some other sort of separator to kind of delineate fields. You may also use variable length data with length fields. So that's usually just the number of bytes and then the data, and then a number of bytes and then that number of data and so on. So keep that in mind as we go through the case studies. Common crypto mistakes in web applications, and this is what we're going to be targeting. The first one, proprietary or homegrown encryption algorithms. This one's probably self-explanatory. Don't try to make your own crypto up and be better than people who have been looking at stuff for years and years and years. People still think that they can do this successfully, and they usually can't. Insecure cipher mode is a big one. Like I mentioned before, using that weak ECB mode rather than CBC or OFB or any of the other more secure modes. Poor key selection, insufficient key length. These are all things that you hear about more often, I think. Insecure use, incorrect use of the crypto API, that comes down to a lot of understanding of what you're actually doing when you're calling some function to encrypt something. What is the default mode? Like how is this actually operating? Do you really understand what the crypto API is doing, or are you just using it and looking at the data that comes out and saying, okay, it's not readable, so it must be working. So here's where we're going to kind of start talking about the techniques that we can use to look at the unknown data. So we're looking at a web application, and we're looking at a cookie that's gotten issued by the app, and we're trying to figure out, what is this thing? What is this blob? So the first kind of thing you can do is to start looking at the length. Is the length, well, kind of the first step, is the length the same as a known hash algorithm? So is it 32 bytes? Okay, maybe it's going to be MD5 or something. Maybe it's a straight hash, maybe it's an HMAC. Just one thing to keep in mind, those common lengths of things that various algorithms spit out. Obviously, if it's a hash, one-way hash, we're not going to be doing too much with it. Is the length of the encrypted data a multiple of a common block size? So looking at the cookie, is it 8 bytes, 16 bytes, 80, or is it something that couldn't be a multiple, like 37 bytes or something? If it is a multiple of a common block size, then that might tell you that there might be a block cipher under here. Does running random-looking pieces of data through some form of entropy measurements show any sort of patterns? So one thing you can do here is just script up a little thing to grab a bunch of tokens repeatedly, and then run them through just basically a statistical analysis to see if there's an abundance of bytes at the low end or the high end, or theoretically something that's truly random should be completely it shouldn't really show any peaks or valleys in terms of distribution of bytes. Some of the automated web app products do this, I think, with session IDs, but not so much with other pieces of data. Okay, another thing we can look for, are there any blocks of data that seem to repeat in the same encrypted message over multiple encrypted messages? So if we've determined that this is a block cipher because it's say 64 bytes, and we've broken it down into 8-byte chunks or 16-byte chunks, can you find any places where once you've broken it down on those block boundaries, the same block appears more than once? That's definitely a sign of ECB mode. There's some tricks you can play determining block size and trying to modify single blocks, swapping blocks between messages, and kind of just see what the application does, see how it reacts. Does it completely barf, or does just because it can't decrypt the thing at all, or does it still work, but you notice that your email address is now different in the profile page or something. Do multiple encrypted messages begin with the same block or series of blocks? A lot of times when you're using a secure mode such as CBC, you'll have kind of a top-heavy looking token where the first couple of blocks are the same across multiple tokens, but then after that it kind of diverges and everything else changes. And if you remember, the reason behind that is if you change the one block of one bit or byte of plain text, that affects all the ciphertext after it. So typically you'll see that sort of pattern where there may be some similarities at the front end, but then it kind of you don't see any of it after that for like the rest of the token. If you see something like that, that's not a definite indication that it's CBC, but it's something to kind of keep in your head as you're trying to figure out, is this thing exploitable or not? Now here are the, as opposed to the kind of the passive things that we were talking about before, these are more of the active things that you can do with regard to the token to try and understand what's going on. So does the length of the encrypted data change based on the length of some value that you can supply? So the very common example in a web application, let's say there's just some piece of data in, say, your profile information that you control that is somehow, for whatever reason, stored in a cookie. So let's take your email address, for example. If I change my email address in my profile to something that's 1 byte longer than it currently is, does my cookie increase by 1 byte? If I increase it again by 1 byte, does it increase? Does that increase mirror itself in the cookie? Or can I just keep increasing it byte by byte, and the cookie stays the same, but then at a certain point, the cookie jumps 8 bytes in size? Well, that's going to be a real good indication of not only that there's a block cipher in use, but also what the block size is, because it's going to jump by a certain amount. How does the encrypted data change in response to user-supplied data? What different fields that I have control over can I use to affect the token? So is it just the email address, or are there other things that are being stored in there? It's kind of a binary way to figure out, even though you don't know how it's being stored, what is actually being stored in there. And then also, if I change one character in a particular piece of input that I know has an effect, what do I see? What's the type of change that I see in the cookie? So if I change one character, is it a 1-character change, or do we see an 8-character change, or does the whole thing change? And that'll give you a better idea of what's underlying. Okay, so that was the sort of the intro, and the rest of this is case studies, and hopefully it'll tie together some of those concepts. Sorry? Can the encryption engine be used in Oracle? Is the application using the same encryption mechanism in multiple places? So if I have control over one, can I change something? Can I use it to figure out what's the encrypted form of blah, and then use that somewhere else in the application where it's decrypting using the same mechanism? Okay, so this is a standard web application that we're looking at. This is a fetch of the My Account page, and the only important thing to look at here is just the fact that we're passing over 2 cookies, EM cookie and an EE cookie. And just, I guess I should also make the point that everything in the case studies is from real-world pen tests, but it's been heavily sanitized to change the names of cookies and make sure that all, any information leading to a particular website has been removed. So what we notice as we're going through the application, just using a standard web proxy tool to look at the requests that are being issued back and forth, we see that the EE cookie is reissued on each request. So every time I request a new JSP page, I get a new EE cookie. The old ones still remain valid for a certain period of time. So at any given time, I may have hundreds of EE cookies that will be accepted by the application. I don't know, just a side note. So I was supposed to say, well, so what does that look like in terms of encoding? If you look at the character set, you probably recognize that it's using upper and lowercase alpha, 0 to 9, and then a couple other characters plus slash and equals, and that's kind of your standard base 64 character set. So the first kind of thing that we will do is just base 64 decode that, and see if we can immediately read stuff in there, which is, it's nice, the nice slam dunk, but unfortunately we can't in this case. So we decode it with base 64, and now we get some equally weird looking garbage. So if we go back now to those passive techniques that I talked about, we'll look at the length of this and see, okay, does it correspond to any known block size? Is this a multiple of 8 or 16? If you break it down, you'll see that it's in chunks of 8, 8 bytes at a time. So okay, maybe this is a block cipher. And we captured way more than 8 of these. I mean, we probably captured about a couple hundred of these at least, just to gather enough data. But 8 fit on the screen. So looking for those sort of patterns in the blocks, one of the things that we mentioned before was looking for repetition. So you usually end up having to stare at these things for a little while, but or put it through some other script that's kind of keeping track of which blocks appear and how many times they appear, and you can do some heuristic calculations like that. But when you do that, you notice that there is some repetition. It's not so important that the block in red appears at that same position in 6 different blocks. What's important is that it shows up in position 4 and position 6 in that first block. And similarly with the blue one, you see a repetition at different positions in the token. So a real cryptographer could probably tell me what the chances are of that happening in a CBC mode or something like that, but I'm going to say it's really low. So I'm thinking at this point that this might be an ECB mode cipher. So now going to the active techniques, determining what is in that thing. We noticed in looking at the broken down blocks on the previous screen that the only variable blocks are really the last 2. Actually, I should just go back a second. You see that the first 5 bytes, the first 5 blocks pretty much stay the same across multiple tokens, and then the last ones kind of switch around a bit. And we talked about how at any given time a bunch of cookies were valid, and eventually they time out. So maybe that last 2 blocks are some sort of timestamp mechanism. So we want to figure out if we could actually affect the contents of this token and how it would be affected. So we registered another account in the application with a really long username, C times 32, which is just, if you don't know, the Perl notation for 32 Cs consecutively. I'll use that syntax a few times in this case study. So when we registered another account with that long username of Cs, you can see what the token is that we got back there. So initially, if you look at that, what jumps out at you? Well, it's longer. It was 7 blocks before, and now it's 11 blocks. That seems to correspond with my longer username. Also, the repetition of some of those blocks, so I see that underlined block in red appears 3 times in a row. So that repetition kind of mirrors that repetition of characters in the username that I chose. So now we know that we can affect the contents of the cookie with our username, and we know sort of what part of the cookie is affected. So now we can kind of refine that a little bit. So we'll register another account with a shorter username, but still repetitions and still C's, so C times 16 in this case. And we look at the token that we get back, and we get back 9 blocks this time. So, which is good, because we decreased the username by 16 bytes, and that resulted in a 16-byte shorter token. And you can see that in comparing that to the C times 32 example, you still have that same block appearing in the token. So it's a pretty good guess that that thing that starts in 1941 is the encrypted form of 8 Cs. The question you might ask yourself at this point is, for the first example, for the C times 16, why don't we see 2 of those? And for C times 32, why don't we see 4 of them? Why do we see? So the guess here, the theory at this point, is that maybe the boundary where the username starts in the plaintext is not exactly on a block boundary. So maybe the username starts like here, and so that it goes from here to here, and it doesn't correctly perfectly align with the block boundaries. And you can see there must be between 1 and 7 characters at the beginning of the plaintext causing that username to be offset. So we want to figure out what that offset is. Okay, this is the one that's usually the most confusing, but it will make sense in a couple slides. So we want to figure out what's going on in that first block? What is the offset? So we can figure out exactly which byte the username starts on, and that'll help us later. So what we did is we created a bunch more accounts, which was nice in this particular application. You could just, self-registration, create as many accounts as you want. So we created additional user accounts with specific usernames to try and determine what the padding was in that initial block. So we have our all C's example, but then we created one that, for example, started with one C and then a bunch of D's, and then two C's and a bunch of D's, three C's, a bunch of D's. And by doing that, we can take advantage of being able to compare blocks between tokens and understand where the boundary is. So you see that with all C's, our first block is the same as when we start with 6 C's, but when we start with 5 C's, it's a different first block. And the best way to visualize that, what's going on, is like that. So if you have 5 C's and then a D, that you must be altering that first block in such a way that, that's why it comes out as a different value. Whereas if you have 6 C's, that's the same first block as all C's, and so you have the same, you have the identical block there starting in DD. So now we have kind of an idea of where the username lives in this token. So we don't really know what's after it, and we really don't know what's before it, the 2 bytes before it. What we do know is it's an authentication token. So, if I can alter this somehow to reflect a different username than myself, then chances are I'll be able to impersonate another user of the application. So now we want to figure out, how do we manipulate this token in such a way that we can do that? So through a different vulnerability in the application, we were able to do a user enumeration vulnerability. So just identify whether or not a certain username exists, or get a list of users. I can't even remember which case it was now. But despite that, we know that a user exists named siteadmin, which sounds like a good one to go after. So to impersonate this user, what we have to do is to obtain the valid ciphertext blocks to construct that cookie. So knowing the offset that we just determined, that there's 2 bytes at the beginning before the username and then a bunch of stuff afterwards, that's what we're looking for. The first block is going to be the encrypted form of 2 unknown things plus site AD, and then the next block is going to be MIN, and then whatever else the application decides to put there. We don't really care, again, what that is. So what we'll do is we'll register one user called siteAD00. There was a minimum length requirement of 8 characters for the username, so that's the zeros. And another one called 000060 min. And
can you just register 6 C's and then siteadmin?
Sorry, well, no, because if you registered 6 C's and then siteadmin, the S would line up with the beginning of here rather than here. So you need this first block that has the unknown plus the first 6 letters. Yeah, exactly. So when we register those, that's what we get. So you can see the blocks that we're interested in are highlighted. We want the site AD block from that one, the MIN block from that one. The other stuff, who cares? So now we can impersonate that user theoretically by combining those two blocks that form the username, and just using the remainder of the token. I think we just picked the remainder of the token from one of those other blocks because we didn't think that it mattered. And lo and behold, it didn't matter. You change your EE cookie to this value, base64, encode it back to its original form, of course, and then you're able to access the application as that user. So here's the interesting part. Thinking back on that attack, what we just did was successfully subverting the authentication mechanism and breaking that crypto without any knowledge of what algorithm was in use, what the key was, what the key size was, anything really, other than all we did was look at some patterns in the ciphertext and make some observations and do a little bit of analysis to try and figure out where something was, but really, we don't know anything about the crypto other than the mode that was used. This could be AES with a 256 bit key. I don't know. So the primary failings here are, number one, the algorithm mode. So you're using ECB mode instead of something else. So we're able to kind of take blocks from different tokens and just kind of stick them in at will without modifying the rest of the token. And the other thing is there's no verification mechanism to kind of for the application to associate specific values of the cookie with a particular username. They're just decrypting what's coming over and finding that known location in the plain text and saying, okay, this is who I am. So in conclusion, ECB mode should not be used, blah, blah, blah. I'm not going to talk too much about that because we have more interesting case studies. So a stream cipher example, that was a block cipher. We can find similar weaknesses in stream ciphers using the same good old pattern recognition techniques. Okay, another different application. In this case, we found a bunch of tokens in URLs that we didn't know what they were. And they were all over the application. It wasn't just one cookie. It was parameters that were passed back and forth with requests. There was one called statement, one called file, context, and there were a bunch of others that in a similar looking format. That's not to say that they are the same format, but we're kind of doing reconnaissance on the application. For all intents and purposes, they're the same. So what we noticed is that, first of all of them changed every time we logged onto the application. And they were never the same for any 2 sessions or any 2 users. So that's just an observation at that point. It's not really telling us a lot, but it's something to kind of keep in the back of your mind. So again, it looks like we're looking at base 64 here, and we're going to choose to start out with this one that's called statement. This lets you look at this was kind of a page where you could see your previous bank statements, and when you click over, there was a link, and it would show like the statement number, and then the actual link had this parameter in it, this long thing that theoretically maps up to the original statement ID in some way. So here are the base 64 decoded values for several of those different statement tokens. So just looking at a first glance, you'd see some similarities. Above that underlined, in each case, I have what the actual statement number was as presented by the web app. So we can use that to start drawing some correlations between the plain text and the ciphertext. If it is ciphertext, we don't even know at this point. So staring at that for a little while, definitely longer than a few minutes, that jumps out at you. So some of the statements, and it's lucky for us that the statements were numbered in this weird way where some of them began with completely different ranges than the others. I'm not sure why that happened, but regardless of that, when it starts with 704.432, we notice a corresponding chunk in the cipher, let's just say the token for now, in the token, that kind of maps up to that. So every time I have 704.432 in the plain text, I have 8B whatever in the ciphertext at that particular location. Similarly, when I have 673.199 as the start of the statement number, I have that corresponding blue chunk at the same place in the token. So that gives me a good idea of where the statement number is represented in the token. So now let's take a look at the remaining 4 digits of the statement number and see if there are any parallels there. Appreciate this slide. It took a long time to make. So when a 1 appears at position 7 in the plaintext statement number, you see an F6. This is the green one we're looking at in the token. And you can draw similar parallels for other bytes. So when there's a 0 there, there's always an F7. Oh look, 0 is F7 and 1 is F6. Interesting. When there's a 7 at the last character, the yellow, there's a 26 there. So you can kind of see that we now know exactly where those 10 characters are in the token that represent the original statement number. The other thing to realize here, I mean, you know it's a stream cipher because my slide at the beginning said stream cipher, but now what we're looking at is you can definitely see correlations, single byte correlations between the plaintext and the ciphertext, and that gives you an idea that this is not a block cipher. So this may be a stream cipher, or maybe this is just an XOR with just a long static string. The interesting thing there is that it doesn't matter to us. If it's a key stream that's generated by a stream cipher, it's still a long list of things, still a long list of bytes that we're going to XOR. So,
They use
yeah.
the same or no initialization vector for all of them.
We don't know. I mean, you can get
But it's not different for every single one. Otherwise, you wouldn't be able to.
right. There's not a different initialization vector for each one. That's right. But in terms of whether they're using one at all, you can't tell. You just get a key stream. So we've made that kind of observation now between the plaintext statement number and the token. So let's try and figure out what the key stream is. So we know that in a stream cipher, the plaintext and the key stream are combined together using XOR, and that's how you come up with the ciphertext. So we know two of those things, and with XOR we can find out what the other one is. So we know that we know what the token looks like, and we know the 10 bytes that represent the statement number, we think. So we XOR that with the ASCII equivalent of that plaintext statement number. So what's in green there, 37, 30, 34, 34, those are the ASCII values representing those digits. And you XOR those together, and you get the 10 bytes shown in blue that I've labeled partial key stream. So we think that that is at least 10 bytes of the key stream, offset by however much into the token. We'll just do a sanity check just really quickly and just make sure that if we take that partial key stream that we think is a partial key stream and we XOR it with those corresponding bytes in one of the other statement tokens, that we do in fact come up with the ASCII value that corresponds to the plaintext, and you can see that we do. So that's all great and everything, but we've got a bunch of statement numbers, and we can XOR all day and not really get anywhere because it's the statements are still at the same location in the token no matter what, so you're not really getting anything beyond those initial 10 bytes. And while 10 bytes is great, it doesn't help you decrypt other things. So this is where it comes in handy that the application used a bunch of those different similar looking tokens that I mentioned. So I mentioned the statement and file and context and a bunch of others. So we said, okay, well, maybe these are encrypted using the same key stream. That's a common mistake, so let's try that. So we take one of the context cookies that we found. Actually, it was a parameter, not a cookie. But we take that, we XOR that with those position of bytes of the partial key stream that we've recovered, just to see what it comes up with. Maybe it'll come up as garbage, but it turns out that it comes up with ASCII. So cool, right? You can kind of guess what might possibly come before that and what might come after it. It also helps that when we were on the app, that when we captured this, particular token, that we were actually on the personal information page. So, even if you, aren't very good at Wheel of Fortune or whatever, you still kind of know what it is. So here's what we can do. We can start to derive more of the key stream based on things that we can guess. So we're going to guess that the plaintext, at least part of the plaintext there is personal information. We still don't know what's before it or after it, but what we can do now is we can get that many more bytes of the key stream by XORing those things together. So now we've gone from our original 10 bytes of key material to gaining an additional 2 bytes on the front and an additional 8 bytes on the end. So now we have 20 bytes of key material. Great, but we still don't have all of it. So you just kind of go through this process iteratively in this case. Took the one token called file. Took our 20 bytes of key material that we know, decrypted it, and came out with what you see in green there, more ASCII. And And this one, you can sort of guess some of it. Maybe not be able to guess what's at the beginning, but it helps that as users, end users of the web application, we knew that we were looking at a part of the application called Help Center. It was, just providing, I frequently asked questions or stuff about this particular page that we were on, which was Paychex. So we'll guess a few more bytes, 3 more in the beginning, 4 more on the end, and now we've got 7 more bytes of key material. So that's the last iteration that I'll actually go through on the screen here, but needless to say, we had a lot of tokens to go through, and eventually, we were kind of able to derive, just through inference like this, enough of the key stream, using those different tokens, enough of the key stream to be able to deal with any length token that the application was creating. So again, we don't need the whole infinite key stream. We only need as much as the application requires for the longest thing that it's encrypting. So eventually we got, I think that was about maybe 150 or 200 bytes of key material. And then we could kind of decrypt everything, all those tokens in the application, and kind of start to try and understand what was going on, what the application was actually passing around now. So statements was the first thing we kind of looked at. And the fully decrypted statement tokens were structured as follows. And if you remember from the earlier slide, values with specific delimiters. So we have a bunch of numbers separated by pipes, and that's probably what the application is parsing on to break down those particular fields. So we have a number, we don't know what they are, or what their significance is rather. Statement ID, number, and then some letters. So, the first thing, again, go for the slam dunk first, and then if not, then actually go back and try and think. Will the application just let us replace the statement number with another valid statement number and view the contents? So replace one of the valid ones with, replace one of the other statement tokens with another valid statement ID that we know of that doesn't belong to us, belongs to another user that we have access to. Change that field, leave all the other stuff the same because we don't know what it stands for anyway, and view the contents. Didn't work. So we're forced to go back and try and understand a little bit more about the structure of that token. The first thing people do to usually protect against you messing with the tokens like that, other than the encryption, is an integrity check on the plain text. So we're thinking maybe maybe these letters at the end are some sort of integrity check against all that other data. So that if you change one of the bytes of data in the earlier part, you've also got to maintain that integrity check on the end. Otherwise, the application is going to calculate it and determine it doesn't match. Someone must be messing with this. Throw out the request. So at the end of each token, we see 4 letters, look like base 64. 4 base 64 encoded characters equate to 3 actual decoded bytes, or 24 bits. Thanks to Google, it turned out that this was a standard CRC24 algorithm, which you just searched for and found the reference code. It was about, 10 lines of code or something in C, and just ran it through, just compiled it, and threw in one of the plain text tokens and see what came out. And it was CRC24, reference implementation. No secret in there or anything. I mean, the CRC is intended, for transmission errors and things like that, not so much for prevention against people manipulating stuff. Because if there's no secret there, it's just a calculation that I have to make. It's not really protecting very much. So we determined that we've got, in a given token, we've got plain text followed by the CRC24 of that particular plain text, base 64 encoded. So, so this is kind of our step-by-step how to build a token from scratch. So you generate the desired plain text of the token. What do you want to be in there as your plain text? Or manipulate an existing token, like we took a statement token and just changed the parts of it that we wanted to change, and leave the rest intact. So somehow we come up with a plain text version of a token. We calculate the CRC24 of that plain text, using our reference code and append it to the end of the token in base64 encoded form. So those 4 characters that we saw before. Encrypt the token by performing an XOR of the plaintext with the key stream that we recovered in the earlier steps. So that's, that's our process of encrypting. And then finally, base64 encode that encrypted token so that it's in the same format as what we originally saw. And when you do that, you can see other people's statements. You can view files in the system. You remember the file parameter. Not any file. I think we were constrained by permissions, but still, you could see a bunch of files that you shouldn't be able to see. And we were able to manipulate the application in a number of different ways by virtue of being able to just construct tokens that the application was considering as trusted, because they felt that the crypto couldn't be broken. So the recap. Again, we were able to successfully subvert the encryption mechanism without any knowledge of the algorithm or the key. Like, think about that for a minute. Like, it's actually kind of cool. Like, you don't have to know anything about it. Like, you just look for some patterns, and you've broken the crypto. I don't know, kind of cool. It turned out that it was RC4, and that was more for kind of our curiosity than anything else. What is this? Are you just XORing with a static string that's hard-coded in your app, or are you using real crypto? So they're using RC4, and they were generating a unique key on every user session, which doesn't matter to us because we can just go through that same process for a given session to figure out what the key is. And actually, once you know what the value of one of the really long tokens is, you don't have to go through that whole iterative process. You just look for that one, and then just generate the key stream based on that one piece of data. So the failings here are the reuse of the key stream across many different tokens that are used for completely different purposes, and the lack of any sort of integrity check. The CRC24 is not going to do it because there's no secret involved there. So that was breaking Stream Cipher. Let's check on time. We might actually make it. So third case study. And this one, I'll say up front that there is no crypto in this one whatsoever. We've done the block, we've done the stream, but this is, you know how we talked about making up your own stuff, your own algorithms, and your own crypto, and security through obscurity, basically. So that's kind of what this example is, but it's kind of a fun one. And the important thing is that the techniques, just the sort of observation, pattern recognition, analysis techniques are the same as in the previous 2 cases. Okay, so here's an application we're looking at. This one was a retail application. So in your profile, you had information stored about you and your credit card and things like that. Through a separate vulnerability in the application, different SQL injection error, we were able to dump the content to the database. Hundreds and hundreds of tables, but these were the ones that were interesting. So you can see that that one table contains maybe a number and some stuff about me, and I should have changed my email address before I switched companies. The shopper table is the one that kind of looks interesting because you see the word Visa in there, and a bunch of dates and a bunch of asterisks that you usually use to mask out credit card numbers, and 4 digits, and I don't know. It looks more interesting. Definitely some privacy and compliance issues when storing credit card numbers, if there's any way that they can be recovered easily. Anyway, so we try to break down that data. And the credit card that we had stored in our profile was just generated using one of those tools that just generates credit card numbers that satisfy the Mod 10 requirement for calculation. So in the database, that particular field that ended in Visa, that's the one that we're looking at. So in the database, when we changed our credit card to that, we saw that. So we can kind of clearly see where the expiration date is at the beginning there, because that's the expiration date we put in. And we can see what the last 4 digits are that match up there right before the word Visa. But you know, the stuff in the middle, what is that? It doesn't seem to correspond to the original credit card. I mean, I don't see any obvious mappings there. So we want to figure out kind of what that is. So we changed our card number to 4 and all ones, which is great because that's sort of the simplest form of the credit card number that still passes the check, and it's what all the applications typically use with testing. But anyway, so we changed our card number to that, and then we checked what was in the database after that change was made, and then repeated this process like a bunch of times to see, first of all, is it the same in the database every time I change it for a given card number, or does it vary? And as you can see, it varied. It's the same card number going in, and the stuff in blue on the left and right is the same, the 4 digits and the expiration, but the stuff in the middle changes. And take a look at all the ones that sort of appear in the unknown section. Well, that definitely maps to the plain text, and maybe that wasn't as evident in the previous case because there was just a varying distribution of characters in the digits in the original card number. But now here, clearly we see a pattern. And if you count up all the ones, it adds up. And there's just some other garbage that's being sprinkled in there, and you can see that even the garbage appears sequential. You can see 1, 2, 3, 4, 5. It's just the positions at which those pieces of garbage actually appear. So, this suggests that what we're looking at is some sort of transposition, a reordering of the original digits. So we've got in the middle section there, we've got 30 digits, and the credit card is only 16 digits. So we have to figure out what's real and what's noise. So we scripted up the credit card number changing operation and retrieving the value from the database, and did that a few hundred times. And upon looking at the data a little bit more closely, we saw some patterns that kind of came out with relation to the 2 characters coming right after the expiration date. So we noticed that anytime those 2 characters were 04, there was a kind of a commonality in the structure of the transition, or the way the data appears in the red section. And similarly for 44, 65, and any other digit between 00 and 99, we saw kind of a pattern of, hey, look, most of the ones appear in the same place. So right there, all of the digits in the original card number are highlighted, so are bolded. So all the 4s and 1s are bolded. So you can see in most cases, so take the top block, the 04 block. In most cases, the bold sections appear at the same locations in each of the 3 examples. There are a few cases where they don't. So that's going to be a case of, well, am I looking at a real one, like one of the ones from the credit card number, or am I looking at just a piece of noise that just happened to be a 1? So if you take the intersection of those locations in each case, in other words, where there's a bold character in each one of the examples, that will kind of help you eliminate where the noise is and where the real characters are. So now we can look at one of the tokens that starts with 04 and see that, okay, the digits that appear in the original card number always show up in these positions, and the rest of it is garbage. And similarly, you can do that for the other mask indexes, let's call them. Okay. Since we know we're dealing with some sort of reordering here of the digits, because we didn't see patterns in our first card number, we got to figure out how are they ordered. And a credit card number with a bunch of 1s isn't going to help us figure out the ordering. So we generated a few more credit card numbers, and then went through that whole process of scripting it up, changing it in the database, and pulling out the ones that correspond to a similar mask index. So in this case, key index number 97. So we pulled all those out and looked at what resulted from 3 different credit card numbers, our original one, and then 2 more ones that we generated using that same tool as before. So now what we hope to be able to do is draw some sort of mapping between the digits in the obfuscated or reordered card number and the digits, the position of the digits in the original card number. And you could totally do this programmatically, but rather than writing that, it was easier to just mark it up on a graph. So what we're going to do here is see how the 4s are underlined in the second card number there. We're going to take those digits from the original card number, and this top, the columns here correspond to the digits in the obfuscated card number as underlined in green up there. So we're going to put an X anytime a particular digit appears at a particular position in the original card. So for example, the first one, a 4. A 4 in the reordered one appears at positions 1, 4, and 9 in the original card number. And then we have to do that for each one of the 4s in the reordered card number, just because we don't know which one of those is the right X. We're kind of laying out all the possibilities here. And we do that with the zeros as well. So a 0 appears at positions 2, 5, and 6 in the original card numbers. We put X's in those spots under the appropriate columns. So we do that for all the remaining digits in that card number as well. And we come up with this pretty graph that looks like that, and some of those X's will be the right X's and others won't. So we do the same thing with the second card number, and we get a completely different looking graph because they're just different combinations, and the numbers appear at different places. So what we want to arrive at eventually is the actual map that has a one-to-one mapping between the reordered number and the real card. So we take the intersection of those two graphs. Another slide that took a long time to make. Ready? Ooh. So those are, since you can't tell, they are in bold, but those are the points where the intersections are. And so you know that those are the places that are the real locations, and the other stuff are not. So now that you have this intersection of the mask, and so first of all, you know which locations the digits appear in, and now from this graph, it's going to tell you what the ordering of those digits is. So you can just read it across. The rows, remember, are the position in the original card number. So you take first position, where's the X? 4, okay? First one's a 4, second one's a 0, and just follow the X's over, and you arrive at the original card number. So that was just, obfuscation. It works. We just make sure that it works for the second card number too, and all our work isn't in vain, and it does work. So recap is that, it appeared that there were 10 different mask sequence numbers. So, we talked about 00 through 99. There actually were only 10 of those. So like all the 90s were the same, for example. Once those were determined, any retrieved encoded value from the database could be decoded to recover the original card number. This was just obfuscation, not any form of encryption. The developer had staunchly defended this code for several years, saying that no one could reverse this. It's safe. I don't need to use encryption. And security through obscurity foiled again. So like I said, that was just kind of a fun example, but you can see how some of the same techniques were applied in terms of analysis. And that is the talk, and I think we have a whopping 2 minutes for Q&A, and I will be hanging around a little bit afterwards, so any questions?
Excuse me.
Yeah.
Are there any automated tools that can analyze the data, trying to recover the encryption or avoiding compression algorithm using?
Yeah, I mean, if they were using a compression algorithm, the question was, what if there's compression used as well as the other things? I mean, if it's a standard compression mechanism, you could try running it through some standard things like, a gzip or things like that, but it just comes down to trying some different things until you can get the data into a format that looks like something that looks like something useful. So first of all, if you put it through gzip and it doesn't throw a big error at you saying this is invalid, then okay, good sign. And you might try that with a number of different compression algorithms. Luckily, in these cases, people don't usually use compression in their cookies, because you don't really gain that much from it. So it's just another layer that you'd have to deal with. Yeah?
Have you at all tried to automate this process?
If only. I mean, there are certain things that you can do that I mentioned before with regard to kind of looking at where, where there's repetition of blocks, and you can kind of script up things like that. But, every application is so different that finding out where those correlations are is really, really tough to automate. If anybody ever does that, then they're going to make a lot of money. Done? Okay, thank you.